Let's work through something concrete. First, I would like to show you the example of a particle in a one-dimensional well. This is entry-level quantum mechanics, and I start at this point because you're very familiar with it, and it will let me illustrate the first two steps in a quantum simulation process. Imagine that you have a particle located on a one-dimensional axis, and there's some potential v of x. Particle is somewhere delocalized in here. Let the scale of this be from minus d to plus d or so. And the particle is governed by a Hamiltonian, which is of the form p squared over 2m plus v of x. So this is the energy of a free particle, the kinetic energy. This is the potential energy. And in analogy to what you saw over there with molecules, this is the set of t terms, and this is the set of v terms that are canonical in a molecule as well. So this is a very simplistic scenario, but it's not all that far away from the more complicated molecular Hamiltonian. And the first step that one employs in simulating the dynamics of this physical system is to discretize. So normally we'll have some continuous set over the infinite one-dimensional axis. So you can imagine that these are some coefficients that you have. I have this complex conjugated. Okay, dx. So this is now expanded into eigenbases of position x. And the natural thing for us to do is to replace this with something discrete, like k delta x, so that this is in some way now going to be a sum over some coefficients, c sub k, of k delta x, where we choose the delta x to be sufficiently small and defined over this discrete interval from minus d to d. Okay? So many of you have done this, especially if you're doing a computer simulation of such a particle in a potential. It should be very comfortable. The second thing that you do is to be able to simulate the Hamiltonian. So you evolve the system. Now, how does one evolve a system under a Hamiltonian? The problem is that this Hamiltonian here is comprised of two parts, h1 and h2, and they don't commute. So I cannot just let my evolution e to the minus I ht. I've dropped all my h bars today. I cannot simply let this be e to the minus I h1t e to the minus I h2t. I cannot evolve with one Hamiltonian, then evolve with a second Hamiltonian, even though they're added here, because they do not commute with each other. And this should be something that you're very familiar with, and therefore we have to apply an approximation.